Good morning, everybody. My name is Bob Steagall, and I'm here to talk about one of my favorite topics, kind of a strange topic, fancy pointers. I call this talk Fancy Pointers for Fun and Profit because I thought the profit motive might bring more people in. I don't know how much fun they are, but actually I don't know how much profit they might bring you, but I like to think of this as stupid allocator tricks as well. All right, so a little overview of the talk. I'd like to begin the talk with a discussion of a couple of motivating problems, the reasons why I am doing this work. I would like to talk about addressing and allocation and presenting the concepts of addressing in a slightly more generalized fashion than you might think of when you think of doing operations on ordinary pointers. Then we'll look at a few framework classes and the implementation of a synthetic pointer. I call them synthetic pointers. Some people call them fancy pointers. I like synthetic because it sounds fancier than fancy. I'll take a brief detour because I get questioned a lot about the performance costs of using synthetic pointers. So I'll spend a couple of minutes with some graphs that I drew up for you, looking at speed of a couple of pointer types with GCC and Clang and Visual C++. Then I'll present a couple of examples of what I call relocatable heaps, which is sort of the culmination coming from the motivating problem, and a little summary at the end. Okay, so the motivating problem here is that of persistence. Suppose that I have a set of types or objects, I guess objects of given types, and those objects have container data members which could possibly be nested. And suppose I have a large number of those, and those things have time-consuming copy construction or ordinary construction or traversal operations. And I would like to save those things to persistent storage on a disk or some other medium. I would like to take those data structures and I would like to transmit them somewhere else. So how do you accomplish those things? Well, the obvious solution is serialization. We're all familiar with that. We've all written code that serializes data structures to disk or reads data from disk and unserializes it. So in the general case, the first step is to iterate over your source objects and serialize them into some intermediate format, like JSON or YAML or XML or protocol buffers or some proprietary format. And if you think about it, the purpose of this serialization is to save important object state. Not all of the state in your objects is important, but what you try to do when you serialize is save that stuff that is important so that when you unserialize it later, you get back the information that you're interested in. Step 2, you deserialize the intermediate format into some sort of destination objects. So you saved it into an intermediate format and you deserialize it into destination objects. And of course, the purpose of this is to recover important object state. Our post-condition for this operation is that each destination object in the destination process, which could be a different process, is semantically identical to the corresponding source object. And I like to think of this as traversal-based serialization because you have some objects that have some structure, you're traversing that structure, whatever it might be, whether it's just members in a class or it's some deeper hierarchy of nested containers, perhaps. So if you think about this intermediate format that I mentioned, the intermediate format can potentially provide several kinds of independence, if you will. It can provide architectural independence, things like byte ordering or class member layout or address space layout. For example, an intermediate format that goes from Wintel to PowerPC would need to provide that. The intermediate format can provide a form of representational independence, where you could have a format that allows one to change from a list of vector of char to a list of strings, or an interlanguage representational independence, where one might go from a list of string in Java to a list of string in C++. Another kind of independence is that of positional independence, where important state is preserved when the destination object exists at a different address in a different destination process. So when you're doing traversal-based serialization, there are costs, as we all know. Usually in C++, because we don't yet have a standard mechanism for compile time or runtime reflection, at the end of the day, you have to write some code or have it generated for you, as the case may be. You have to be able to traverse the source objects and render them to your chosen intermediate format. You have to parse the intermediate format when you want to deserialize and reconstruct your destination objects. And if you've ever written anything more than trivial than this case, you know that how easy it is that this kind of code can quickly become fragile and complex. There's also a temporal cost. With serialization, typically you have some sort of data stream and you have to read it end to end. Unless you have some specialized functions that can pick up the data stream in the middle to do the deserialization. There's also a spatial cost. Most common intermediate formats are verbose. JSON is pretty verbose. XML is the poster child of verbosity. Another risk is that private implementation details of your data objects might be exposed. Things that you may not want to be exposed. You may be accidentally displaying information that you don't want the customer or competitors to see. And finally, because of this, encapsulation of your objects might be violated. Someone might be able to fiddle with the intermediate format and then cause problems when your code is deserialized. So let's revise the problem statement a little bit and narrow it down. Suppose that I don't need architectural or representational independence. In other words, my source and destination platforms are the same, and by that I mean OS and processor. Suppose that my class and member layout is going to be the same on the source and destination platforms, i.e. I'm using the same compiler in both spots, or compilers that are close enough that this is a match. Suppose that I can use the same object code, even, on the source and destination platforms. Well, I would like to be able to implement kind of object persistence that does not require me to write any sort of special per-type serialization or deserialization code. A kind of persistence that allows me to persist standard containers and strings without going to any special effort. I would really like to use fast binary operations like write and read or send and receive. So the idea that I've been working on for some time and I continue to play with in the background when I have some spare CPU cycles is what I call relocatable heaps. So I define a heap as being relocatable if it can be serialized and deserialized with simple binary I/O, whether it's write and read or send and receive or fwrite and fread. And after deserialization at a different at a different address in a possibly different process, the heap continues to function correctly and the heap's contents continue to function correctly. So how do you make this work? Well, you go down another layer because at the end it's turtles all the way down. And you define, or you make the prerequisite that every object in a relocatable heap must be of a relocatable type. All right, so what's a relocatable type? I consider a type to be relocatable if it is serializable by writing raw bytes and is deserializable by being able to read raw bytes. And if a destination object of that type is semantically identical to its corresponding source object, regardless of the destination process and its address in the destination process. So what kind of types are relocatable? Well, Given the prerequisites that I've laid out here, integer types are relocatable. Floating point types are relocatable. Standard layout types that contain only integer and floating point types, and 0 or more other standard layout types which themselves contain only integers and floating point types are relocatable. There are several kinds of types that are not relocatable in my definition. Ordinary pointers to data are not relocatable. Why? Because the data to which they refer may exist at a different address or not even be present in the destination process. Pointers to member functions, static member functions, or free functions are not relocatable because the object code to which they refer is almost guaranteed to exist at a different address in the destination process. Types with virtual functions are not allowed, or I don't consider them to be relocatable because their vtables will almost certainly exist at a different address in the destination process. Types or values of relocatable types that express some sort of process dependence are not relocatable. And here I'm thinking of things like file descriptors or Windows handles. I mean, by definition, a process-dependent handle is meaningless outside of its own process. So let's talk about them in practice. How do we design these things? Well, we need to provide methods, member functions, to initialize, serialize, and deserialize the heap. We need to provide methods to store and access some sort of special object that resides in the heap, and I think of it as being a master object, that acts as a gateway to the objects of interest in the heap. On the source side of the equation, I need to ensure that my relocatable type requirements are observed by all the contents that I want to put into the heap. I need to construct the master object that I just referred to in the heap at some special or known address so that anyone that wants to use the heap can find that master object. I need to allocate the stuff that I want to be persistent from that heap, and I need to make sure that it is in some way accessible through the master object. And I need to be able to serialize the heap. On the destination side of the equation, of course I need to be able to deserialize the heap, and I need to be able to obtain access to the heap's contents through that master object. And that's why the master object is supposed to exist at some offset or known address inside the heap. Someplace inside the heap that any process knows where to go to find the master object. So let's think about addressing and allocation. When I think about the problem of allocating memory, I see 6 aspects. I want to say concepts, but that word is heavily overloaded these days. I see 6, and aspects is probably not the best word. I see 6 not quite orthogonal aspects to this problem of not only addressing, but also memory management. And I also see them split into 2 broad categories. The first category is one that I call structural management. And I sort of think of it in 4 layers: the addressing model, the storage model, the pointer interface, and the allocation strategy. The second broad category that I think of is thread safety and transaction safety. If you're running in a multi-threaded environment, you need to make sure that your pointers and your heap do the right thing. If you happen to be writing an allocator that's going to be used in a database where transactional integrity is required, you just made the problem even more difficult. So let's talk about the addressing model. I think of the addressing model, and I call it a model, but it's really a type. I think of the addressing model as being a policy type that implements primitive addressing operations, somewhat analogous to a void star. Its purpose, analogous to a void star, convertible to a void star. Its purpose is to provide access to raw memory segments that are going to be provided by the storage model. We'll get to that in a second. The addressing model defines the bits that are used to represent an address. If I have some opaque type, my addressing model type, there are going to be bits in it. And the addressing model determines how those bits are used to represent an address. We all have an intuitive idea how the bits in a void pointer or a char star are used to represent an address. Well, this is just abstracting that a little bit. The other thing that the addressing model defines is how memory from the storage model is arranged. With ordinary pointers, the storage model is trivial. It's a linear address space that is natively known by the processor in the C++ machine. The addressing model can be represented in a number of ways. Of course, I just mentioned the one that we're all familiar with, the void pointer, the void star, aka natural pointer. Another representation is a fancy void pointer, or a synthetic void pointer, or a pointer-like type, as the standard refers to them. And as I mentioned, because there's this intimate relationship between the addressing model, which represents how to do addressing and understands the layout of memory, it's usually closely coupled with the storage model, which is going to provide memory in that layout, that arrangement that the addressing model expects to see. The next aspect that I see is that of the storage model, which I mentioned before. And I think of this as a policy type that manages segments. Some allocators, if you've ever looked at allocators, some of them refer to what I call segments as superblocks, meaning these are the big chunks of memory that are grabbed from the operating system. The storage model interacts with some external source of memory to get these big segments, and it borrows them for a while, and at the end of your program, after main exits, it will give them back. The storage model provides an interface to those segments in terms of the addressing model. In this picture, my conception of this is the lowest level of allocation. There are actually two levels, getting segments and then allocating chunks. So a segment, as I mentioned, is a large region of memory that's been provided to the storage model from some external source. And so here are some examples. You got break and sbreak for process private memory in Unix. You've got virtual alloc and heap alloc, which are the analogs for Windows. You've got shmget and shmat for System 5 style shared memory under Linux and Unixes. You've got create file mapping and map view of file, which are the analogs for shared memory under Windows. A very important part of my conception of this world is that of what I call the pointer interface. And this again is a policy type that wraps the addressing model to emulate a pointer to data. If you can imagine you had a class, a very simple class that contained a void star as its data member, and you wrote a wrapper around it to implement a T star. Well, the pointer interface is analogous to that wrapper, and the void star in this analogy would be the addressing model. So the idea here is that it provides enough pointer syntax so that the standard containers can function. It provides conversion in the right direction to ordinary pointers. So if you have a T star, you can add CV qualifiers to it, like const and volatile, and those are trivial conversions. It is convertible in the right direction to other pointer interface types. So if I have a synputter of base and a synputter of derived, I should be able to trivially cast my synputter of derived to a synputter of base, just like I can cast a derived star to a base star trivially. In a way, it extends the interface that's defined in the standard for random access iterator. And so the most trivial representation of a pointer interface is in fact that of a T star, or a natural pointer. And again, I call these synthetic pointers, and the standard calls them pointer-like types. Another aspect of this is allocation strategy, and I think of this as being a policy type that manages the process of allocating memory for clients. It requests segment allocation and deallocation from the storage model. It interacts with those segments in terms of the addressing model. It divides the segments up into little chunks. And here I've defined a chunk as a little region of memory carved out of a segment that the allocator's client is going to use. It provides those chunks to its clients in terms of the pointer interface. And it is analogous to malloc and free, or operator new and delete, or any of the custom allocators that you can drop into your process. I also mentioned briefly the aspects of thread safety and transaction safety. Thread safety, correct operation in the presence of multiple threads. transaction safety, supporting basically ACID semantics, rollback, or allocate, commit, rollback. When I think about any heaps implementation, I sort of see this picture. The addressing model, storage model, pointer interface allocation strategy are a set of layers, and the concurrency aspects feed into that. They're typically not very simple relationships, and because they're not simple, I'm going to not talk about them here other than to briefly mention them. So let's talk about an example addressing model, offset addressing. In this case, putter 1, putter 2, and putter 3 are instances in some buffer, some heap, that are pointing to a string, foobar. And each of these pointer objects contains an offset from the pointer's location, the pointer's address, to the address of the first character in the string. So you can see putter 1 contains an offset of 36. If you add 36 to 8, you get 44, which is the address of foobar. If you add 24 to 20, you get 44. If you take 72 and you add minus 28 to it, you get 44. This is a very useful thing. If you've ever used boost inner process has a type that's part of it called offset putter. And my offset putter is very heavily influenced by the groundbreaking work that boost inner process did several years ago. Why would I want to use this? Consider a self-contained DOM. And by this, suppose that I have some tree-like data structure, structured data, not necessarily a binary tree. I would like to put this thing in a buffer, and I would like to have the tree in the buffer exist correctly. So on the left, in the blue, you see the data elements that define, the data members that define a simple binary tree. The little blue section called to the right of alloc is the heap. And you can see that the nodes from the tree are allocated in the heap, and they're hooked up together so that one could start at root and by dereferencing the pointers, traverse the tree. In this particular example, the buffer that all this exists in, or the region of the heap in which all of this exists, is address 4096. And so I would like to send this somewhere else and have it all be connected and work correctly, perhaps at another address like 131.072. Another addressing model is what I think of as being two-dimensional addressing. Suppose that you have a backbone array of pointers, and each of those pointers points to a segment that's come to be connected to the backbone via the storage model. And in this case, in this particular example, imagine that it's in private address space. And my segments are pointers to UNT stars, and the segments, I treat them all as unsigned chars. Another way you could think about these segments is, very similarly, is in shared memory. I can use some sort of shared memory allocation mechanism to create shared segments, and then I can map them into my private address space just as if they were segments that were actually part of the private address space. And this gives me the ability to define a tree that exists in shared memory. Now, when you map shared memory segments into local memory, there's no guarantee that the operating system is going to map a given segment to the same address in two different processes. And so I've tried to indicate that at the bottom by the fact that the addresses on the left are different from the addresses on the right. And yet we want to be able to go to the root of the tree from either process and traverse the tree. So a brief mention of pointer-like types. These are mentioned 4 times in the standard, but the only real substance that defines them is in the requirements for nullable pointer. See table 28 in N4687, which is slightly outdated. But these types have to fulfill several standard requirements: quality comparable, default constructible, copy assignable, destructible. The same requirements that an ordinary pointer would have to meet. They have to have swappable L values. Default initialization may produce a partial result, and if you use it, it could lead to undefined behavior. Value initialization of a pointer-like type must produce something which is equivalent to a null result. Construction or assignment from a null pointer has to produce a null putter has to produce a null result. and it must be contextually convertible to bool. Certain fundamental operations, I'm not going to list them all here, they're in table 28, may not throw exceptions. So as I mentioned before, there are limitations with fancy pointers. There's a runtime cost. The fancy pointer arithmetic, which we have to implement in our code, is not going to be as fast as that of ordinary pointers. Casting is limited. With fancy pointers, you can only use static cast because static cast is the only kind of casting that's allowed to generate or invoke code. You can't const cast, dynamic cast, reinterpret cast, or do a C-style cast. But that's okay because we only need static cast to implement the containers. And all of the container implementations, Microsoft, Clang, GCC, they all use static cast internally. So I'd like to talk quickly about some framework classes. I'm going to show you some code, not lots of pictures, but it's all very simple code. Keep the pictures of the addressing models in mind that I just showed you a couple moments ago. So I'd like to talk about two addressing models, the two that you saw at the top of the presentation, offset addressing and what I call based 2D extra large addressing. And when I put the presentation online, on my GitHub, there will be code which demonstrates other two-dimensional addressing models, not just the one that you're going to see here. I'd also like to talk briefly about how one actually builds a synthetic pointer class that mimics ordinary pointers as closely as possible. All right, so I mentioned, and we described before, the idea underneath offset addressing. So really, written in code, and this is pseudocode, by the way. This is not really, well, I suppose it could be valid C++, but it's not good C++. So the idea is that the address that's returned by dereferencing the synthetic pointer is equal to the address of the pointer itself plus the offset that it stores. And it goes without saying that the offset that's stored in this pointer has to be assigned type because the offset could be negative. The thing that's being referred to could exist at a lower address than the pointer itself, as is the case with putter 3. So the requirement is if I dereference, in this example, putter 1 and putter 2, I dereference them and I take the address of the result, I should get the same answer because they're both pointing to the same thing. But what makes offset pointer and fancy pointers different is if I actually do a memcompare of the pointers themselves, they don't have to be equal. In this case, putter 1 and putter 2 have a different set of internal bits, and yet they're pointing to the same thing. They have a different physical representation, but they have the same semantic meaning. So, how do we do this? Well, here's an example, the top of the class declaration for the offset addressing model. And in the presentation, I will bold things of interest, and I will highlight them in yellow if they are of strong interest. The reason I put this up is I wanted to show you the special member functions for this. All of the constructors and assignment operators. You can see that the special member functions themselves, except for the default constructor, the special member functions in this are non-default. In fact, all of the constructors and assignment operators for the offset addressing model are not defaulted. They all have to be implemented, except for the destructor. There are also some member functions to do critical operations, computing an address, decrementing, incrementing, and assigning from some other address. In terms of data members, the only data member is a type of difference type, or putter diff t, and this is the thing that maintains the offset. And I want to show you three member functions. A static member function which computes the distance between two void pointers, and then member functions which an instance of the addressing model, of the offset addressing model, uses to find the distance between itself and something else. So at the top is the code. It's very simple to compute the distance between two void pointers. And here I was experimenting and I used reinterpret cast of int putter t. I probably could have static casted to char and done the same computation. But that's a static member function, which then is used by the other two member functions, which are not static member functions, that allow an instance to find the offset either to another instance or to a void pointer. And you can see that in both cases there's a branch. On the bottom, if the argument is a null putter, then we internally store the null offset. Otherwise, we store the offset between this object, the target object, and whatever that void pointer is. In the middle, if the offset of the other object is the null offset, again, we store the null offset. Otherwise, we compute the offset between this object and the other guy. And the reason we use a null offset, which is not 0, is because it is legitimate for a pointer to be able to point to itself. Think of a linked list. Think of a linked list node that's empty and a sentinel node which points to itself to indicate that the list is empty. So we choose an offset of 1 to represent a null pointer because it's very likely that another pointer is going to point 1 byte inside the representation of another pointer. This is actually the strategy that's used by Boost Offset Putter, and I have to say I think it's brilliant. In computing the address, if we have the null offset, we return the null pointer. Otherwise, we reinterpret cast to void. We take our local address, we add our offset to it, we cast it to void star, and we return it. And I've got a couple of other helper functions for assigning to the target from some source. So you can see our constructors very quickly. The default constructor we construct from the null offset. Otherwise, in our constructors, we're computing the offset from the other thing to us. And likewise for assignment, we're computing the offset from us to the other thing, and we're using that internally as our offset. For our two-dimensional addressing models, I'm going to go back and show you the two-dimensional addressing view. So here I've got my backbone of pointers, I've got some segments, and I happen to have another array which tells me the size of the segment, so I know if I'm doing an addressing that's out of bounds. And my data is going to lie at some offset from a segment, and if you've ever worked in DOS or Windows 3, you probably see where this is going right away. So when I know James is probably knows that. So the address is equal to a segment index plus the offset into that segment. And so I can store a pointer in this two-dimensional array as two integers, a segment index and an offset. So what does that look like? I'm not going to show you the whole storage model here. I'm just going to show you the interesting parts, which are the static arrays, which contain the segment pointers, the backbone, and a member function called segment address. So the member function at the bottom, given a segment offset, returns the base address, segment ID returns the base address of that segment. So in the addressing model, which uses that storage model, here's the top of the class declaration. In this particular class, all of the special members are defaulted, but construction from addressing models and assignment from addressing model and null putter have to be implemented. Again, the four important member functions: computing an address, incrementing, decrementing, and assigning from somebody else. And at the bottom, there is the offset and segment that together allow one to compute the address. And I call this extra large because they're both 64-bit integers. So a pointer in this particular model is 16 bytes instead of 8. So if I want to compute an address, it's very straightforward. I have my segment ID and my address. I look up the base of my segment, give them the segment ID, I add the offset to it, and I return it. This actually turns out to be pretty fast. If I have to assign from, it's a little more complicated. I don't expect you to read through all of this, but assume I have some void star and I want to see if I can assign it to an instance of this particular type. Well, I actually have to loop and look through each segment and see if this void star exists within the boundaries of one of those segments. And if it does, great. I I can figure out what the segment ID and what the offset is inside the segment. If it doesn't, well, then I'm just going to say that it's null. The pointer interface is something that looks very much like a random access iterator. And so you can think of the header as being defined in split into several sections: special member functions, other constructors, other assignment operators, conversion operators, dereferencing and pointer arithmetic, and helpers that support all of this. One of the key things to make it all work is using some SFINAE to enable particular member functions in certain circumstances. So we've got a few helper traits here. The first helper trait allows me to enable member functions when an implicit conversion is possible. The second is the logical inverse of the first. What that means is this member function will be enabled if an explicit conversion is required. The third the third trait helps with performing comparisons, making sure that I'm not comparing the address of an int to an address of a string, which is a meaningless comparison. The fourth trait helps with disabling operators when the pointed to type is void. So I can't use, for example, the pre-increment operator if my fancy pointer type is representing a void. So I use SFINAE to remove that from all overload resolution sets. And the fifth one helps with determining what the pointed to type is. So I'll try to get through this quickly. So at the top of the synthetic pointer class, you can see that the class is a class template. It's parameterized on T, which is the type that it's supposed to point to, and it's also parameterized in terms of an addressing model. And in this case, we'll look at the offset addressing model, and maybe we'll get to the 2D addressing model. I've got a rebinder, which is something that's used with stood pointer traits to make it easy to work with allocators and the allocator-aware containers. I've added a random access iterator tag so that this thing will be seen by the standard algorithms as being a random access iterator. My special member functions for this wrapper are all defaulted, which means they rely on the special member functions of the addressing model type, the second template parameter. I have some user-defined constructions. If you look carefully at this, what I'm attempting to do is to only allow implicit conversions to compile, only allow implicit conversions at compile time. So the first two are implicit conversions from an addressing model and also from a null pointer, a null putter. The second two are conversion constructors, which are enabled if conversion is possible. So if U star is convertible to a T star, then using SFINAE, this constructor will participate in overload resolution. Likewise, for the bottom one, if U star is convertible to T star, that constructor will participate in overload resolution. If T star is void, SFINAE will make those things go away as if they never existed. And there are similar uses for the assignment operators. We can always assign from a null pointer, but again, if U star is not convertible to a T star, then SFINAE will make those last two assignment operators disappear from overload resolution. And a similar principle is applied to conversions. We only allow implicit conversion in the second case if U star is convertible to a T star. I'm sorry, if T star is convertible to a U star. That's the only time we allow implicit conversion because we want the syntax to be natural. We don't want to have to specifically cast in the case where we wouldn't cast if it was ordinary pointers. The top case, the explicit operator bool, this requires a static cast except in qualified contexts. So if this pointer is actually used inside the parentheses as a predicate in an if or a while or a for, it's as if the explicit didn't exist. It will implicitly cast to bool, which makes it very nice for logical operations. Otherwise, in any other context, there must be an explicit cast. And I have operators for dereferencing. Now notice I'm using different traits to do SFINAE here. In this case, I am only enabling these operators if T is not void. Because if T is void, I can't have those operators. And likewise with the pointer arithmetic operators. It gets a little messy. And yes, so the increment, decrement, and assignment equals. All right. And these are some helper functions that are part of the class. Finally, at the bottom of the class, as I alluded to before, there is an instance of the addressing model, whether it's that 16-byte segment offset wrapper that we saw a couple minutes ago, or it's the offset addressing model which contains a single signed 8-byte integer that we saw before that. The synthetic pointer, the synputter, wraps the addressing model. The addressing model provides a void star interface. The synputter wraps that and applies an appropriate typed interface. And if the type of the synputter is void, it does the right thing. If it's non-void, again, it attempts to mimic natural pointers. There's also a friendship relationship in here for cousins. That allows other types of synthetic pointers to do construction, implicit construction. I'm not going to worry about that now. Running a little low on time. So just I wanted to mention how the address computation is used by the synthetic pointers. So if I'm converting to a U star on the top there, you can see I'm using my addressing model. I'm calling the address member function of that, which returns a void star. I'm statically casting it to U star, and that's how I get my typed pointer information out of it. And very similar for the structure dereference operator and the star, the dereference operator. Very quickly, I get asked about synthetic pointer performance. I did some testing with these two models, two different data types, a uint64 and a test struct, which was something with basically randomly generated data, 64 bytes of randomly generated data, 13 different array sizes, 100, 200, 500. The pattern repeated up to 1 million. I tried to sort them with std sort with 3 different compilers. These particular results were computed on this laptop, Core i7 with 16 gig of RAM and Windows 10. And then the GCC and Clang results were running on a virtual machine on here. I used std chrono to do the timing. So copy operations were repeated 10 million times. So if the array was 1 million, had 1 million elements in it, sorry, the sorting operation. Sorting operations were performed 10 to 100 times depending on the array size. Clang and GCC both used libstd C++ for the sort. All the results I'm going to show you are ratios. So for sorting 64-bit integers using Clang, you can see that the performance of the 2D extra large model is very close to that of ordinary pointers, whereas the offset model is quite a bit more expensive, as you would expect, because there are branches in the dereferencing operation. For the test structure, the performance is about the same, and here again, as I said, it's a larger structure that has lots of data in it. For GCC, we see a very similar behavior of the performance curves. For the test structure, with Visual Studio, for sorting 64-bit integers, the performance was a little bit worse, and I'm not sure why. I didn't look at the object code or the disassembler, but this was with all optimization turned on. So I don't have a good explanation for that. The ratios, however, for the test struct were a bit better in this particular case with Visual Studio. So this gives you some idea of the performance degradation that you might encounter if you're using synthetic pointers. And again, in the case of sorting 64-bit integers, the cost of copying an integer that the sort does to swap them is very low. And I chose this particularly because I wanted to emphasize the performance decrease that you see from the synthetic pointers. I didn't want the synthetic pointer degradation, performance degradation, to be lost in the cost of working with some very large structure. So the tests were shown to make the overhead from the synthetic pointers look worse than it would, I think, in most situations. So we come to the demo portion. What I'd like to do is run a quick demo here of the self-contained DOM problem that I mentioned at the top of the talk. So what I'm going to do is I'm going to define what is effectively a storage model, which I call SCD for self-contained DOM, the SCD raw heap. And the raw heap is going to contain just a buffer in it. And it's going to have an integer in it that tells me the high water mark in the buffer. And I'm going to allocate from that buffer monotonically. I'm going to start at the bottom and keep adding. I'm never going to deallocate. And the high water mark tells me where my next allocation is going to come from. And I have a member function for allocating and deallocate. Deallocate is a no-op. And I have a member function to round things up. So at the bottom, you can see what the allocation algorithm is, as I mentioned. I compute a void pointer from the base of my buffer and my high water mark in terms of my allocation size. I round that up to compute the next high water mark, and I return that void pointer. Now I have to actually, to make this work with the standard containers, I actually have to create a conforming allocator. In this case, I've called it SCD allocator. This is an allocator for objects of type T, and the N, which is used there, is used to specify the length of the buffer for the heap that we just saw. So you can see the first line there, I'm defining what my heap type is, and I'm saying I want a heap type that has n bytes in it, and it's going to be resident in this allocator. And the rest of these nested type aliases are what you might see in any conforming allocator. I've put the rebinder in here because I find it easier to do that than having to redefine stood allocator traits. Of interest here is actually constructing an allocator from a pointer to one of these heaps, and I misspoke before. Let's see. Yes, the heap is a member of the. So stored in the allocator itself is the heap. Okay, so I'm going to define a message type. That's the thing, the buffer that I mentioned before that I want to send somewhere else. So I'm going to define an allocator, and I'm using type defs here just to keep the code simple. I'm going to define a string type, and here simple string is a class that I'm not showing you here. It's a very simple implementation of something that's supposed to act like a basic string or a stood string. The reason I don't use stood string is because stood string is not yet allocator aware. It's a defect in the standard, and Arthur O'Dwyer and myself are working to remedy that. But it has like a C-stir member function. I'm going to create a list inside of this buffer. So I'm defining an allocator for the list. I'm defining a list in terms of that allocator. And now I'm going to define the pieces that I need to support a map. So I want to create a map of string to list of strings. And all of these things that I'm defining here are getting to the last line here. I'm going to create a stood map of sin string to sin list, and sin list is a list of sin strings. And I'm going to use this less operator, and I'm going to use the allocator that you saw on the previous slide. Inside my message, I'm actually going to have my heap, and I'm going to have an instance of my map. All right. Now, looking at the class interface for message, there's one member function, very quickly, add data. This is the thing I'm going to use to put data in the map. So the member function, I declare the allocator and the string and list allocators using the address of the heap. I am going to declare a working string and a working key string and a value string and a working list. I'm going to add data into the list. I'm going to make up a string and add them to the list. Then I'm going to put data in the key string. And then finally, I'm going to take the key string and the list of strings, and I'm going to in place construct them into the map. My demo function, this is my actual test function. I'm going to create the message. I'm going to add data into the message. I'm going to print the values. Then we're going to do something crazy. We're going to do some more crazy stuff, and hopefully you'll be impressed by what it does. So give me just a moment here, and I'm going to bring up a virtual machine. All right, so this is an executable. It was, oops, it's not coming. Hold on. Okay, now we should be able to see it. Okay, this is an Ubuntu 18.04 virtual machine. I've got GDB set up to run on the right. All right, so there's the test function that I mentioned. We're going to step into that test function. All right, so I am going to instantiate my message type with a buffer of 8,192 bytes. I'm going to add some data to it, and I'm going to take a detour into this function quickly. So here I'm creating an instance of my string allocator, my list allocator, by passing to them the address of my heap. I'm creating a working key string, a working value string, a working list. Now I'm going to create value strings, and I'm going to push them onto the list. Now I'm going to create my key string, and I'm going to assign my key and my value, which is a list of strings, into the map. In return, and I'm not going to do that again. All right, so if everything has worked correctly, I should be able to print out 4 of these objects. Hopefully we will. Okay, so you see on the left are 3 of those objects. 3 entries in the map, the key strings that were created, and the lists of value strings. And I want you to pay attention to the addresses on the right-hand side. And clearly these are very high addresses, so you can see that they are indicates that they've been off the heap somewhere. I'm sorry, off the stack. All right. Now, if you look at the code, I've got a buffer of bytes, and my buffer, which I call bytes, is the same size as my SCD message objects that I instantiated at the top of the function. And I'm going to do something incredibly rude, the kind of thing that your parents warned you against when you were teenagers, and they said, you know, if you drink, you're grounded for a year, but if you cast object, if you memcopy objects, you're grounded for life. We're going to do that. All right, I'm going to memcopy that object, SCD or MSG. I'm going to memcopy it into this buffer. I'm going to do something rude again. I'm going to const cast that, or I'm sorry, I'm going to reinterpret that to a pointer of that same message type, and I'm going to attempt to print those values. And I've just printed the values. Now look at the addresses, compare the addresses between the top and the bottom. Different addresses. So what I've done is I've taken source objects, I have built them in a way that is both a legitimate C++ object and a pre-serialized bag of bytes. And I've memcopied that pre-serialized bag of bytes to another location. I've gotten the address of it. In fact, I've found the master object, if you will, by doing that reinterpret cast. And I'm able to iterate over it as though it were a fully constructed object. In fact, it is a fully constructed legitimate C++ object. And just for giggles, I'm going to do the same thing with a stood vector. So here I have a stood vector of char of the same size, the size of my MSG SCD message. I'm going to mem copy into that stood vector of bytes, or char. I'm going to do the ugly reinterpret cast again, and I'm going to attempt to print. And there you go. You can look at the addresses. These addresses are very low, indicative of being something that was allocated on the heap. So why do you care about this? Why is this a useful technique? Why do you need to know about it? I'm currently working in the field of distributed stream processing, and we spend a lot of time passing data from one node to another, and a lot of our CPU cycles are being burned up with JSON serialization and deserialization on the order of 20 to 30%. And those CPU cycles don't need to be used. Our data is simple enough that we could use this technique and not have any JSON serialization or deserialization. And likewise, I think there are a lot of problems in messaging out there where the data is simple enough that this technique can be used. Now remember, the relocatable heap is just basically integers and floating point types. And a lot of problems can be solved just with integers and floating point types. And the standard containers, the allocator-aware implementations of them, the good allocator-aware implementations of them, will support this very robustly. Okay. So, in summary, synthetic pointers and relocatable heaps are a lot like parachutes. You know, we're not all Army Rangers jumping out of airplanes. This is a very specific kind of hammer for a very specific kind of problem. But I think it can be useful. It's very useful in those situations. For my money, the possible applications I see for this are relocatable heaps for private use. Suppose that you have a game engine or game state that you want to save, and you have some data structure which is amenable to being relocatable. You could construct your game state inside that data structure, and then serialization is writing it to a disk with, say, fwrite, and loading your game state back into memory is as simple as calling fread, and your objects are ready to go. As long as you can pay the runtime cost of traversing your game state and pulling the stuff out of it you need, save and restore could be very fast. The next application I see of relocatable heaps is for shared memory, specifically shared memory databases. The company I used to work at before, we used techniques very similar to this to implement a shared memory database, where we had a reader process and a writer process. And the reader process was consistently reading from the database, and the writer process was periodically updating data inside that database. It was a fully ACID database, and had transactional and concurrency. It was transactionally and concurrently safe. And we used principles very similar to what I've just shown here. Self-contained messages and DOMs, I just demonstrated that for you. I think the usage for that is fairly obvious. Something I've played around with a little bit, but it's probably not useful to a lot of people, is creating a highly instrumented debug allocator. This is more to satisfy my own curiosity. One could instrument allocations and deallocations, but think about what the synthetic pointer does. You can also instrument individual pointer operations. You could count how many times a pointer is dereferenced, or how many times it's incremented, or how many times it's compared, because now you have an inside track into the guts of the pointer, and you can control it, you can measure it at any point you want. I don't know if that's a very useful thing to do, so I'm just throwing it out there. So finally, this is a work in progress. I do a little bit more every year. Stay tuned. Questions? We've got 30 seconds left, so time for maybe one or two questions.
What about cross-platform issues with different Indian nomenclatures and int sizes?
The question is, what about cross-platform issues when you have different Indianness, different architectures, different object code? So at the top of the presentation, I said this technique, I specifically constrained it to the case where object code is exactly the same on each platform, requiring basically the same processors, the same operating system to work. This is not a general technique for cross-platform data sharing. Yes?
In the offset pointer implementation, why is the null offset 1 and not the negative address of this?
So the null offset is 1, or the null offset is 1, which represents a null pointer for a very specific reason. So let me explain by giving an example. Suppose you have a linked list, and you are representing an empty linked list by having a sentinel node, which is a common technique. And to represent an empty linked list, the sentinel node points to itself. Okay? So if the sentinel node points to itself, then the offset of the pointer to itself is 0.
So I'm not suggesting 0, I'm suggesting the negative, whatever this address is, the negative of that, so that the sum is 0.
Ah, yes, I never thought of that. But the problem is that the comparison for the null pointer has to be this. No, it doesn't have to be the same. That's a good idea. I have to think about that.
Thanks.
All right, one more, and then we've got to get off.
Yeah, one of the issues we run a lot is even if it's the same process, but we have data rested, but the different version of the same binary, and sometimes the structure changes over time.
Right.
So
You have structure layout issues. Yeah.
we need like backward forward compatibility.
In my particular case, all of the executables that we compile and put out on our streaming network are all generated at the same time, and that's guaranteed.
And I was wondering, how would they compare with like flat buffers or Captain Proto? Those.
I have not yet had the opportunity to compare the performance against those. As I said, it's a work in progress.
Okay.
All right, thank you, everybody.